Hey everybody, welcome back. Because 6.5 is so beefy, what I'm going to do is I'm going to bust it up into different little lessons. So it's going to feel like there's 3 lessons to it, which really there is. Actually, really there's like 10 of them because it's such a crazy section. Stuart really chose to get nutty in 6.5. So what we're going to do is we're going to do a lesson on pumping fluids. So I'm going to just make up a problem and let's play with this thing for just a sec. And we're going to get all kinds of jiggy with this in class, but I want to introduce you to this. Let's say that we have a cylindrical reservoir, okay? And let's say that this cylindrical reservoir is, I don't know, 10 meters high. 10 meters high. And it's filled to a height of 8 meters. All right. And what I want to know is I want to know how much work. Oh, I should probably come up with a diameter, right? Let's say the diameter, I don't know, what's that look like, about 6 meters? 6 meters. I want to know how much work is done in pumping all the water out. In pumping, wow, pumping out all of the water. Okay? Now, let's think about some stuff here for just a sec. So it's filled with water, all right? I'm going to have to pump all of the water out of it. So let's think about what we're really doing. It's kind of a misleading problem. What we're really doing is as though it's kind of like you took a straw and you put it at the top and you sucked it all the way down, or almost think of it like a pump that you would put in a pool, where that pump would sit on the top and it would skim all the water off of that and pump it up and out. All right. In other words, it's not going up and then down. It's going straight up and out. So it would be like there's this little hose right here and there's a little pump right there. As the water level decreased, this pump would stay on top. So think about what's happening. Does it take more or less work to pump the water out right here at the top when it's 8 meters versus when it's down here near the bottom at, say, 1 meter? The answer to that, it takes way more work to pump the water when the water height is 1 meter, because you've got this vertical distance that you have to pump the water, okay? So what we're going to do is we're going to have to play around here for just a sec. Hopefully there's a little bell going off in your head that says, well, Ripley, wait a sec. It all depends on what we're pumping, right? I mean, gasoline is less dense than water, which is way less dense than, say, maple syrup. Right? It would take way more work to pump maple syrup. It'd be the strangest reservoir ever. I don't know, maybe they have them that size at the maple syrup factories. All right, so density plays a role. All right, now let's play for just a sec. By the way, the density of water is 1,000 kilograms per cubic meter, per meter cubed. Density, remember, is mass per unit of volume. All right, now let's think about that. If density, this little row thing is used to denote density. If density is mass per unit of volume, then do you agree that mass, now remember, mass is important because work comes from force, and force is mass times acceleration. So mass is equal to density times volume. Well, that's kind of weird. So what does this really mean? This is kind of confusing. Well, let's rewrite what I just said. Force equals mass times acceleration, which in this case is going to be density times the volume times the acceleration of gravity, right? That's the thing that's pulling against your work. And then work is just density times volume times acceleration times distance. Now, let's see if we can fill in. Once we've got force, the work is a lot simpler, but let's see if we can fill some stuff in. Okay? Well, first and foremost, we know what the density of water is. This assumes that it's water. If it's not water, we have to know what that density is. Okay? So we know what that is. We're not afraid of that. What is this volume thing? Well, it's actually really easy, especially in the context of the problems that we've done before. Watch this. Here's what I'm going to do. I'm going to take myself a nice little cylindrical sliver. Okay? And I'm going to figure out the amount of work that it takes for me to pump that disk of water out of this cylindrical tank. Now let's think for a second. Does everybody agree, and hopefully you do, that the distance that I have to pump that thing is x sub I. Now you may say, Ripley, why don't you do it with y sub I? Well, remember, just like we did with the chain problem, it's just let it be x sub I for now. You can call it whatever you want. I'm simple country folk. All right, now think about this. If this is x sub I, how thick is this cylinder? What's delta x? True? Right? Well, what do we know that the volume of that cylinder is? Well, we know that the radius is 3, right? So I'm just going to make some chicken scratch over here, and then we'll put everything together, okay? Okay. Do you agree that the volume of that little disc that I have to pump up, at its absolute simplest, that's exactly what we're doing, is we are pumping that disc up and out. That's what our pump is doing, okay? The volume of a cylinder is pi r squared times h, right? So in this case, this is going to be pi times 3 squared times h, which is delta x. This is just my chicken scratch. Cool? And then the acceleration of gravity, that's what we're fighting against. So let's look. I know that the force that actually, you know what? We can go straight to the horse's mouth on this guy. Look at the work. Let's figure out the work that it requires to get that ith sliver up and out of the reservoir. Well, look at what we got. It's going to be the density of water, which is 1,000 kilograms per cubic meter, times the volume. Hey, we got the volume sitting right here, right? Which is times 9 pi times delta x. This is cubic meters, by the way. Delta x. Now let's include units so we can be sure that what we're going to get is a Newton meter, right? So times delta x. And what are the units on volume? Well, this is going to be meters cubed, right? So that takes care of that. And then let's see. The acceleration of gravity is 9.8 meters per second. Now let's cancel some terms because this is getting a little crazy. Let's see. That goes, or meters per second squared, right? Meters cubed, meters cubed. Look at this. I've got a kilogram meter per second squared. It's actually known as a Newton, right? And then the distance. Well, what distance do I have to haul this thing? I have to haul it x sub I meters. I have myself a Newton meter. I should have given myself more space is what I needed to do. Right? Kilogram meters per second squared. That's a Newton. The distance that I haul it is x sub I meters. So let's figure it out. Now remember, where is the action taking place from and to? I need the overall work. Well, how much work is done? Let's do the integrals, right? First things first, let's see if we can grab some constants. Ooh, yeah. Well, I lied. Let's do 9,000. I'm going to do 9,000 pi times 9.8, right? And then I'm going to have x, because my x sub I turns into x when I add all these things up, times, and my delta x turns into dx, right? Let's make sure we got everything. I got 1,000 times 9, that's 9,000. I got a 9.8. I got an x sub I that turns into an x and a delta x that turns into dx. Fabulous. The question becomes, excuse me, what's my limits? Well, where's the action taking place? My first circle, my first disc that I have to pull out has to go what distance? Well, 2 meters, right? My last one has to go how far? 10 meters. So the action is taking place from 2 meters to 10 meters. Now, students may ask me, wait a second, Ripley, why aren't I integrating from 0 to 10? Well, because there's no action from 0 to 2. So I guess you could say, you could call this the integral from 0 to 10, which is the integral from 0 to 2, plus the integral from 2 to 10, right? Well, we know that there's no work being done. Think of it as though you're lowering the pump into the pool, right? That make sense? Okay, now let's see if we can figure out what the heck this thing is. Oh, good gracious. What is that, you guys? Help me out. Let's see. No, don't even help me out. It's not even worth it. I'll screw it up if I try to do it in my head. 9,000 pi times 9.8 times x squared halves from 2 to 10. Right? So this is, now I'm going to cheat here and do this over on my side because I'm getting tired of looking at it. 9,000 pi times, whoops, not divided by, times 9.8. Ew, good gracious. That's ugly. Let's just go 9,000 times 9.8. 9.8, enter. 8820. I could have done that in my head. What a sissy. Let's see, 88, not 20, 88,200 pi times, let's see, 100 or 10 squared halves minus 2 squared halves. What was that, 48? Or sorry, yeah, 50 minus 2 is 48. So this is going to be 48 times 88,200 pi. Nice. That's an ugly number. Let's go times pi. I'll do all this on the calculator too here in just a sec. Times 48. And that is a boatload. Oh my goodness. This is approximately 13, how many? Good gracious. 13 million. Yuck. So what, 1.33 times 10 to the 7th joules. That is so much work. Think about that. Which kind of makes sense. I mean, think about it like in a space program. You guys know that the most expensive thing about going to space is schlepping your water with you. It takes a ton of work to get water to space because it's so heavy. It has so much force. Remember, a pint is a pound world round. A gallon is approximately 8 pounds of water. Excuse me, 1 gallon. And we need what, 2 gallons a day? But I digress. Let's use our calculators here real quick. I'm going to shrink this guy down, and I'm going to pop this guy up. And let's see, what did we get? I should probably go back a page, make sure that we know what we're doing here. So we're going to go to math, and I'm going to go up to FNIMT. I love this on-screen calculator. And I'm going from 2 to 8, and I'm going to go, ye gads, what is it? 9,000 pi times 9.8. And then we're going to go x, and then dx. All right, that gets it right. dx, and booyakasha. Let's see what we get. Ooh. Oh, now you know why? Look at what I did. I went from 2 to 8. Ooh, so many little tricks that you have to pay attention to in this stuff. So we're going to hit second entry. That was actually very instructional. Let's go back. See if I can get back to my limits. That was an instructional mistake. Ripley, well done. I love it when I screw up like that. Okay, so I went 10 there, don't I? Ding dong. Enter. There we go. Let's see, is that 13 million? Yep, yes it is. So 1.33 times 10 to the 7th is what it smells like. Wow, that's crazy. Now, we're going to do a problem straight out of the book in class. I actually want to do that problem with you because it's kind of a fun one. All right? But this is how pumping problems work. But notice the themes. All right? All we're doing is a variation on a theme. Where is the action taking place? From and to. How does it work? Right? All I did was I figured out what my force was. I did a fancy little trick here by using density to help define mass, didn't I? Remember, density is mass per unit of volume, so mass is density times volume. I figured out that the volume is just this volume of this little cross-sectional disk here. I figured out where I was pumping disks from and to, and then I was done. We're going to do hydrostatic force here in just a second, but I'm going to let you take a breath, and I'll meet you back here in just a moment.